Your Starship is alone between the stars when the most terrifying thing happens. Nothing. One routine check-in goes unanswered, then another, and then the line to Earth is just gone. No error code, no distress call, just a clean, hard silence that never ends. In this video, we're going to pull that moment apart and see what really happens when a Starship loses contact with Earth forever, and still has to fly, survive, and build a future with no home to report back to. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. Even a tiny probe like Voyager 1, more than 20 billion kilometers away, talks at under 200 bits per second. Way slower than an old dial-up connection. But it is enough to say, I'm still here. Your Starship does the same thing, just scaled up. A high-gain antenna, maybe a dish several meters across, locks onto Earth and sends that heartbeat, non-stop, year after year. When contact breaks, your ship does not feel anything. The engines still push, the lights stay on, the air is breathable. Inside you see a small indicator on a console change from link nominal to link lost. Maybe a warning sound, maybe a log entry. It looks like a simple communication fault. You expect it to clear after a software reset, or after the ship swings past some obstruction. There is no physical impact that tells you, this is it, Earth is gone for good. It starts like any routine glitch. Back on Earth, the way people know something is wrong is not cinematic. It is statistical. Ground stations like NASA's Deep Space Network use huge radio dishes, 34 meters, 70 meters wide, spread around the globe, so at least one can see you at almost any time. They point a dish at your predicted position and send out a clean, stable radio tone at a known frequency. Your ship's transponder listens for that tone, locks onto it, and sends it back with your telemetry added on top. In the control room, they do not stare at a picture of your ship, they stare at graphs. One key number is signal-to-noise ratio, basically how strong your signal is compared to the background radio noise of space. Another is bit error rate, how often the ones and zeros in your data are getting flipped or corrupted. When everything works, your carrier signal stands out clearly above the noise, and the bit error rate is low enough that error-correcting codes can fix most mistakes. As you get farther, or if something starts to fail, that changes. The sharp peak of your signal over the noise starts to shrink. The bit errors creep up, then spike. The data stream becomes unreliable, then unreadable. At some point, even a narrow beacon at 10 or 20 watts, the kind of power a small transmitter can send, just blends into the background. Earth keeps the dish locked, integrates the incoming signal for longer and longer, averages the noise to try to pull out any trace of you. The graph stays flat. There is no identifiable carrier, nothing to lock onto, just random hiss. At that stage, nobody immediately says, we lost them forever. Real missions lose signal temporarily, all the time. A solar flare can saturate receivers. A spacecraft can go behind the sun or a planet. An antenna can mispoint by a tiny angle. So the first response is routine. Engineers mark loss of signal as an anomaly, and they start the recovery checklist. They send blind commands, meaning they transmit instructions even though no response is coming back. They tell the ship to switch to a backup radio, to lower the data rate, to go into a simple safe mode, and just send a basic beacon. Ground stations sweep their huge antennas across a small patch of sky, changing the pointing a bit at a time, in case your ship's aim is slightly off. They try nearby frequencies, in case your local oscillator drifted. They adjust data rates, message formats, anything that might re-establish lock. This can run not just for hours, but for days or weeks, especially for expensive missions. For past Mars landers and orbiters, teams have spent long periods doing exactly this, just in case one more command wakes the spacecraft up. There is a point, though, where the recovery attempts hit hard limits. Your ship has only so much power. Batteries deplete, reactors or radioisotope sources decay. Propellant lines can freeze. If the last confirmed telemetry is very old, and models say your hardware should now be far beyond its planned lifetime, the chance that you are still alive drops sharply. The logbook language shifts from anomaly under investigation to no response to all recovery sequences, and finally to spacecraft presumed lost. That is the quiet official way of saying, We are never hearing from this object again. All of that can happen even if nothing catastrophic breaks, because distance itself is the main killer of deep space communication. Radio power spreads out as it travels, covering a larger and larger sphere centered on the transmitter. The same number of watts is now spread over a huge area. If you double the distance from Earth, your signal at the receiver does not just get twice weaker, it gets 4 times weaker. 10 times farther, 100 times weaker. At 1 astronomical unit, about 150 million kilometers, or 93 million miles, the Sun-Earth distance. That is manageable. At 10 astronomical units, out near Saturn, the same transmitter looks 100 times fainter. Now push to 100 astronomical units, then 1,000 astronomical units, on an interstellar path. The faint radio trickle from your ship is competing with the natural radio noise of the galaxy, the sun, the cosmic microwave background, and with electronics noise inside the receiver itself. To keep the signal above that floor, you would need either a huge increase in transmit power or an enormous antenna on the ship, or both. There is a distance where, even with perfect hardware, your signal at Earth is so weak that it cannot be pulled out of the noise. You could increase dish size on Earth, stack more antennas together, integrate for longer, but there is a practical limit. Beyond that, your data is statistically indistinguishable from random static. There is an extra time twist on top of that. Say your ship is 10 light years from Earth when you send the last transmission that actually gets through. That radio wave takes 10 years to reach Earth. When ground control finally receives that packet, they see the status of your ship as it was a decade ago. If they reply instantly, their answer takes another 10 years to get back to your location, if you are still on roughly the same line of sight. So every conversation is separated by 20 years minimum. On board, you experience those years directly. You keep sending health reports. You watch signal quality on your end dropping because your receivers also see Earth getting fainter. There is a specific day from your perspective when you realize, we have not had a valid reply from Earth for longer than the round-trip light time. They should have answered by now. Something is fundamentally wrong. That moment, the psychological break where the crew accepts that Earth is gone for them, can happen many years before Earth's last good data even arrives. So from one frame of reference, Earth's, your story ends with a weak final signal that fades into noise. From your frame, the ship's, the story continues long after that, in total radio silence. The two timelines do not line up, and neither side ever sees the full picture of what really happened in the other place. If the very first thing that happens in this scenario is that your voice quietly falls below the universe's background hiss, the next question is even harsher. What is the physics that makes that silence permanent? And how does space itself work against any last attempt to be heard? Silence in deep space is not clean or empty, it is full of the wrong kind of sound. When your starship loses contact, it is not because nothing is out there, it is because everything else is louder than you are. First, space is noisy in radio terms. Your signal has to fight through a constant background from the galaxy, from the sun, from distant stars, from the afterglow of the Big Bang. Sensitive receivers do not measure this noise in bars, like a phone. They measure it as an equivalent temperature, fractions of a Kelvin, just a few degrees above absolute zero. That number tells you how much random energy is sloshing around in the antennas and electronics. Your ship's transmission has to sit on top of that. A deep space probe signal, even when we can decode it, can be weaker than the radio power from a cheap Wi-Fi router in an apartment on Earth. The only reason we can hear it is because we spread big antennas over tens of meters. We integrate the signal for seconds or minutes. We use heavy error correction, and we know exactly what pattern we are looking for. Your starship, far beyond Neptune, then beyond the Kuiper Belt, is sending something that, at Earth, is far below what a normal human ear would ever notice if it was sound. The receivers are pulling order out of a sea of small random fluctuations. Now take that tiny signal and apply the most basic rule that is working against you. The farther you go, the faster you vanish. Power from a transmitter does not just march forward in a straight tube, it spreads out in all directions, over a growing sphere. The surface area of that sphere grows as the square of the radius, so if you are twice as far, the same power is spread over 4 times the area. In plain language, double the distance, your signal at the receiver is 4 times weaker. Go 10 times farther, it is 100 times weaker. So if your 20-watt transmitter is readable at 20 astronomical units, roughly 3 billion kilometers, about 1.9 billion miles, keeping all the same antennas and electronics, then at 200 astronomical units, which is 10 times farther, the received power is 100 times lower. That drop is not subtle, it is brutal. What was a thin but clear line above the noise becomes a barely visible bump, then just statistical noise. You can try to fight this by making the beam narrower, by building bigger dishes, but the basic rule stays: every extra unit of distance costs you much more than the last one. That is why we use very specific radio frequencies for space communication. Real spacecraft do not usually talk in the same bands as your car radio. They use microwave frequencies called S-band, around 2 to 4 gigahertz, and X-band, around 8 to 12 gigahertz. At those frequencies, the antennas can be a few meters across on the spacecraft, tens of meters on the ground, and still produce a reasonably narrow beam. These bands also cut through the interplanetary plasma fairly well, and Earth's atmosphere is transparent enough there for ground stations to work. For truly interstellar distances, the pressure grows to shift higher. Ki-band, around 26 to 40 gigahertz, gives you even tighter beams for the same dish size, so you concentrate power better. Go higher still, into optical and near-infrared lasers, and you can form beams that are incredibly narrow and intense. A laser at a wavelength of around 1 micrometer with good optics can send more useful power toward a distant receiver than any radio dish of the same mass. But that upgrade comes with a different kind of trap. When your beam is that tight, pointing accuracy becomes extreme. An angular error of just a few microradians, a tiny angle comparable to aiming a laser pointer at a coin hundreds of kilometers away, means that over light-year distances, you can miss the target by millions of kilometers or millions of miles. On a Starship that is rotating, vibrating, firing engines, being hit by micro-impacts, holding that pointing for hours or days is a monster challenge. So the same technology that could, in theory, solve your too-weak problem can also make it very easy to lose the target completely with one tiny misalignment. Even if your beam is perfect, the space between stars is not perfectly clean. On average, the interstellar medium has roughly 1 atom per cubic centimeter, which sounds like nothing. But over light years, that nothing adds up. Free electrons in that thin plasma interact with low-frequency radio waves, stretching and delaying pulses. We see this clearly with pulsars, rotating neutron stars that send out sharp radio flashes. As their signals travel through the galaxy, they get dispersed, high frequencies arriving slightly earlier, lower frequencies smeared out in time. Your ship's radio pulses are subject to the same effect. At very low radio frequencies, your message gets stretched, blurred, and weakened by the time it reaches a distant receiver. You compensate with higher frequencies, but then you run into dust and small grains. At millimeter and submillimeter wavelengths, some of your energy can be scattered or absorbed by tiny solid particles between the stars. Go to optical or ultraviolet, and dust can block or dim you even more. There is no perfect band. You are always trading one kind of distortion for another, and over longer and longer paths, each small effect eats away at the clean, sharp pattern your bits started with. All of that leads to a very hard limit that does not care how good your engineers are. There is a base level of noise in any receiver, from the sky, from the galaxy, from the electronics themselves. That sets a noise floor. Your signal has to sit above that floor enough that, statistically, you can say, these variations are not random, they carry information. Information theory tells you there is a maximum data rate you can achieve for a given bandwidth, power, and noise level. If you try to push more bits through than that, errors explode, and no amount of clever coding can fix it. As your ship goes farther out, with fixed transmitter power and fixed antenna size, the received signal gets closer and closer to that floor. At some distance, your most basic beacon, your slowest possible data rate, is still buried. You could integrate for longer, stack more and more listening time, but that only helps up to a point. When the signal is truly below the noise, every pattern you think you see is just a coincidence. At that stage, your bits are in a strict mathematical sense, indistinguishable from randomness. When you hit that wall, it is not a software bug. It is not a bad day at the tracking station. It is not something you can fix with a firmware update on the ship. It is the physics of signal detection drawing a line and saying, beyond this distance, with this power and this hardware, no one can ever know that you are talking at all. So if the universe itself sets a hard ceiling on how far your voice can carry, and you pass that limit, the next problem gets much sharper. When no one can hear you, how do you steer? How do you navigate? And how do you avoid drifting blind into hazards with no outside correction at all? When Earth goes dark, your navigation system does not suddenly turn stupid. It just loses its external referee. You keep flying, you keep updating your position. But from that moment on, every number you use comes only from what you can see and measure on board. You have actually been dead reckoning for most of the flight already, just with Earth constantly correcting you. Modern probes use star trackers and gyroscopes to know which way they are pointing. A star tracker is basically a camera that looks at the sky, matches what it sees against a star catalogue, and says, you are rotated this many degrees from this reference pattern. Gyroscopes track how your orientation changes between those star tracker updates. That gives you attitude, the direction you are facing, not your position. Position, during the early mission, comes mostly from Earth. Ground stations measure the Doppler shift of your radio carrier. They see tiny changes in frequency as you move toward, her, or away from them, and they use that to calculate your speed along the line of sight. They also do ranging, timing how long it takes a signal to go out and come back to get your distance in kilometers. Combine that with known gravity fields, and they fit an orbit. They tell you where you are and where you will be. When those updates stop, your only absolute reference is the sky itself. You still have catalogues of star positions and proper motions, how fast those stars are drifting across the sky over years and centuries. You can point your star trackers, measure angles between bright stars, and solve for your orientation and rough position. But your orbital solutions are now fully free-running. Your onboard computer takes your last known state, your velocity and position, and pushes it forward in time using your own measurements and your own gravity models. So how do you even know how fast you are moving? Not just relative to your own last estimate, but relative to the universe around you. You can turn your telescopes on known stars and galaxies and look at their spectra. If you know what the pattern of light lines in that spectrum should be at rest, any shift of those lines toward red or blue tells you your relative velocity along that sightline. Do that in different directions, and you can solve for your three-dimensional motion. You can even use the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, as a reference. The sun already moves at about 370 kilometers per second relative to that background, around 230,000 miles per hour. That motion shows up as a small temperature difference in the microwave sky, slightly warmer in the direction we are moving, slightly cooler behind us. Your instruments can measure that dipole pattern and see how it changes over time, which gives you another handle on your velocity. At cruise, your Starship might be doing 100 kilometers per second, around 360,000 kilometers per hour, about 220,000 miles per hour. At that speed, you cross one astronomical unit, the Earth-Sun distance of 150 million kilometers, in about 17 days. Your navigation computer can integrate that forward second by second, building a trajectory. But every measurement has a tiny error, and every burn has a tiny mismatch between planned and actual thrust. Those small differences do not stay small. The longer you fly without outside correction, the more those errors grow. This is where pulsars become your deep space GPS. Pulsars are rotating neutron stars that send out concentrated beams of radio or X-ray emission. Millisecond pulsars spin hundreds of times per second, and the pulses they send are incredibly regular, like cosmic clocks. You can equip your ship with X-ray detectors that watch several of these pulsars at once. By measuring the exact arrival times of their pulses compared to the times you expect from your internal clock and sky model, you can solve for your position in 3 dimensions. This is not just theory. Experiments with satellites in Earth orbit have already shown that using pulsar timing, you can locate yourself to within tens of kilometers without any signal from the ground. Scale that up, use more pulsars, better detectors, and longer integration times, and your Starship can keep its position estimate locked down quite well, even light years from home. Your star GPS does not depend on Earth at all. It depends only on physics that works the same everywhere. But now you hit the next problem. The universe keeps pushing on you in ways that are small, but over long times not small at all. Your engines are never perfectly symmetric. Maybe one thruster runs a tiny bit hotter. Maybe you have a slight fuel leak from a valve that does not seal all the way. Maybe the way your radiators glow in infrared creates a tiny recoil force. Solar radiation pressure. The push from sunlight hits one side of the ship more than the other, at least until you are far from the star. These forces can be on the order of a millinewton, a thousandth of a newton, which sounds like nothing. Your velocity error may be 0.1 millimeters per second. That is 0.0001 meters per second. Basically zero from a pilot's perspective. But give that error time. Over 10 years, which is about 315 million seconds, that tiny mismatch becomes a position shift of around 30,000 kilometers, roughly 19,000 miles. Over 100 years, stretch that by a factor of 10, and now you can miss your target star, or your planned flyby, by many astronomical units. That is why your autopilot cannot just coast on the original plan. It has to constantly observe the sky, compare what it sees to where the model says those stars, pulsars, and galaxies should be, and update the trajectory. It might need onboard radar or LiDAR to scan ahead for larger objects, and optical surveys to spot any bright hazards. You are now your own tracking network and your own mission design team, 24/7, with no one on Earth to sanity check your updates. Then you run into situations where navigation is not just where are we, but do we dare fly this path? On Earth, a gravity assist past Jupiter or Saturn is simulated thousands of times by big teams. They model the planet's gravity field, its moons, its rings, its radiation belts. They choose a closest approach distance that maximizes the speed gain, while keeping the risk from debris low. If something looks off, they adjust the burn, move the aim point, and update the plan. Out here with Earth gone, you do not have that safety net. Say you are approaching a gas giant in a new system. If you pass close, you can grab a big velocity change for almost no propellant, shaving years off your travel time. But that close pass might thread you through a ring system full of meter-scale rocks, or a dense moon swarm at tens of kilometers per second, tens of thousands of meters per second, something like 100,000 miles per hour. A collision at that speed is instant destruction. You can either play it safe, stay far out, accept a slower, fuel-heavy trajectory, or you can dive in, trusting your models and your sensors to be right. There is no team on a headset saying, "We've run the numbers, here's the safe corridor." Every burn is a bet you cannot hedge. If you are wrong, your descendants generations down the line pay the price, because they find themselves off course with no fuel margin. Or they never make it past that encounter at all. So once you are flying blind to the rest of humanity, you can still find your position. You can still aim your path, but every correction is a solo decision, with errors that do not go away. They only grow. The next question is just as hard. Even if your trajectory is perfect, what happens to a crew that has to ride this forever path, with no way home, in a closed metal world that has to be its own planet? The moment contact dies, your ship stops being a spacecraft on a mission and turns into a world with hard walls. There is no resupply run, no emergency launch from Earth, no tanker coming later. Everything you will ever breathe, drink and eat is already inside the hull, or has to be recycled inside it. Right now, the closest thing we have is the ISS. It already recycles over 90% of its water. Urine, sweat, humidity in the air, all of it runs through filters, distillers and chemical beds until it is drinkable again. Oxygen mostly comes from electrolysis, splitting water into hydrogen and oxygen with electricity. Carbon dioxide is pulled out of the air by scrubbers, using chemicals like lithium hydroxide, or by regenerative systems that can be recharged. That's for a small crew in a volume of a few hundred cubic meters. Your Forever ship scales this up by orders of magnitude. You are talking about thousands of cubic meters of pressurized space, more like a small high-rise building than a capsule. To close the loop further, you add algae bioreactors and plant growth chambers. Algae can eat CO2 and produce O2. Plants can do the same. While also turning wastewater and nutrients into food. Human waste is no longer garbage, it is feedstock for the system. The goal is simple to say and hard to reach. Every kilogram of carbon, nitrogen, and water cycles over and over with minimal loss. That sounds stable, but the truth is you are now more like a small, fragile planet than a ship. A stuck valve in a water recycler is not just a maintenance item, it is a threat to your total water inventory. A failure in a CO2 scrubber is not an alarm for the console, it is a countdown on breathable air. With no Earth in the loop, your ecosystem has to not just run, but diagnose itself, repair itself, and adapt as the crew and the environment change over decades. If every breath and every sip depends on machines and biology that never get a rest, then the next hard question is simple. What is feeding all of that with energy, day and night, for generations? On Earth, you do not think about which power plant keeps your next lungful of air possible. On a forever ship, energy is the real currency. Every litre of water you recycle costs kilowatt hours in pumps, heaters and filters. Every kilogram of food you grow under lights costs kilowatt hours for LEDs, circulation fans, nutrient pumps and climate control. Life support is not free background. It is a continuous power burn. An RTG, the kind of radioisotope generator used on Voyager or Curiosity, gives you a few hundred watts to a few kilowatts. Enough for a probe, not enough for a city in a can. A serious Starship needs a fission reactor or fusion system putting out megawatts. A rough high-end estimate for space habitats is around 1 kilowatt per person, just for basic life support and habitat systems, not counting propulsion or heavy industry. For a crew of 100, that is about 100 kilowatts 24 hours a day. That is just to keep air moving, water cycling, lights on, and waste treated. Now add agriculture. Growing food for 100 people, if you rely heavily on artificial lighting and controlled environments, can easily demand hundreds of kilowatts more. Add labs, manufacturing, computing, and your propulsion system, and you are in the megawatt range very quickly. At that point, every decision about who gets power is a trade. Do you put more energy into expanding crops, or into a new sensor array, or into extra shielding for a reactor that is aging? When energy is tight, shutting down a deck or lowering the temperature by a few degrees is not an annoying power-saving tip. It is a survival strategy. A single failure in the reactor, a crack in a heat exchanger, or a drop in output as fuel ages does not just dim the lights, it directly cuts into how many people your closed ecosystem can support at full health. And even if you win the energy game, the environment outside the ship is still hitting you constantly with invisible damage. How do you keep a crew alive when the space around them is a slow radiation bath? Once you are outside Earth's magnetic field, space keeps delivering radiation non-stop. Astronauts in low Earth orbit get some protection from the planet's magnetosphere, but on the way to Mars or cruising between stars, you lose that shield. Measured doses are on the order of 1 to 2 millisieverts per day, sometimes more during solar events. A Mars round trip can give crew several hundred millisieverts. Over decades in deep space, that stacks up to multiple sieverts. For context, a few sieverts delivered quickly can cause acute radiation sickness. Spread out over years, it greatly increases lifetime cancer risk and can damage the nervous system. So your hull cannot just keep air in and micrometeoroids out. It has to be a radiation bunker. Engineers think about shield thickness in grams per square centimetre. To really cut down galactic cosmic rays, you want something like tens of grams per square centimetre, even more for serious protection. Translating that, you are talking about meters of water, or thick layers of polyethylene, or compacted regolith if you carry or harvest it, wrapped around your living areas. Water is especially attractive because you need it anyway. You can store large tanks around crew quarters, effectively surrounding people with a liquid shield. The mass is brutal though, tens to hundreds of tons, but there is no shortcut. Without that mass, your crew is basically living inside a slow CT scanner for the rest of their lives. So you are stacking heavy shielding around a volume that has to support crops, machines, and 100 humans. Even if radiation is under control, their bodies still face another problem. Their bones and muscles were built for 1G back on Earth. What happens when you take that away not for 6 months, but for 6 decades? Human bodies are tuned for 1G. In microgravity, like on the ISS, bones lose density, muscles atrophy, fluids shift toward the head. Vision can be affected. Astronauts can lose 1 to 2% of bone mass per month without aggressive exercise. That is with top-tier training programs, treadmills with harnesses, resistance devices, and careful diet. For missions that last months, not generations. On a forever ship, that is not enough. You cannot expect every person, from children to elderly crew, to spend hours each day fighting gravity loss forever. The straightforward way out is to build artificial gravity by rotation. If you build a ring with a radius of about 100 meters and spin it at around 3 revolutions per minute, you can create a centrifugal effect at the rim close to 1G. That means your floor pulls you down roughly the same way Earth does. At that size, the rim speed is on the order of tens of meters per second, something like a car driving on a highway, wrapped into a circle. For people walking inside, that feels normal, but the engineering is not easy. The structure has to handle constant tension from the spin. It must be balanced, or it will wobble and stress itself. Bearings or magnetic supports that allow parts of the ship to spin relative to other parts must run smoothly for decades without seizing. If the rotation slows or stops unexpectedly, everyone inside goes weightless again, and anything not bolted down becomes a hazard. Spin too fast, with a small radius, and people get motion sickness from Coriolis forces when they move their heads. Spin too slow, and you need a much larger ring, which means more mass, more materials, more complexity. Yet without some form of artificial gravity, entire generations grow up with bones and hearts that may never handle a full 1G environment again, which could matter a lot if they ever land on a planet. All of this hardware sits on top of a living system that we already know is touchy even on Earth. If a small sealed habitat on the ground can drift into trouble in a few years, what happens when your only world is a far larger, more complex version, and the nearest help is centuries away? We already tried a tiny closed world on Earth and nearly broke it by accident. Biosphere 2 in Arizona was a sealed habitat experiment with plants, animals, soil, and a small crew. It was supposed to run as a mostly closed ecosystem. What happened? Oxygen levels dropped unexpectedly. Carbon dioxide spiked. Soil microbes ate more oxygen than expected. The atmosphere inside shifted in ways the designers did not predict, and they had to inject outside air. That was with full access to Earth's labs, spare parts, and outside scientists. Your ship is essentially Biosphere 3 in space, but with more moving parts, more machinery, and a time horizon of centuries, not a couple of years. You have agricultural decks with layered crops, hydroponic systems, biofilters, insect populations, microbial communities, all interacting. A sensor glitch in a CO2 meter could mean nothing. Or it could be the first sign that plant uptake is falling and your loop is drifting out of balance. You will run dense networks of sensors, redundancy on redundancy, and still biology is messy. A fungal outbreak in a main crop, a trace contaminant slowly building up in the water cycle, a fertilizer tweak that works for one generation of plants but destabilizes soil chemistry over 10 years. There is no call Houston, send up a new module option. You detect, diagnose, and fix everything with the people and the tools you already have on board. Knowing that one hidden fault can slowly kill the farm or poison the air while you are decades from anywhere does not just stress your engineers, it gets into everyone's head. You live with the fact that your world is a machine and an ecosystem that can never stop, never reset, never be abandoned. So the next pressure point is not just technical, it is human. How does a crew, and then their children and grandchildren, stay mentally stable when they know there is no home waiting, no evacuation plan, and no outside voice ever coming back on the line? Silence from Earth does not break you in a single day. It wears you down with clear numbers. At first, the crew treats it like a routine outage, a solar storm, an antenna problem, a software bug. You keep logging status reports, you keep queuing messages, you keep sending data packets that no one answers. People say, we'll hear back on the next light time. and they mean it. Then one full round trip passes, then two, then three. The light time delay to Earth might be 10 years, so each "we'll see" on the next reply is a decade. After several of those, the math is simple. If Earth still existed, if it still had power, people and antennas, someone would have responded to at least one of your last attempts. At that point, the silence is not an accident, it is the new normal. That is when the mission patch on your arm changes meaning, even if nobody says it out loud. It used to say explorer, part of a larger human project going out and coming back with knowledge. Now it says exile, because there is no way back and no sign that anyone is left to report to. The date when that flips from hope to acceptance is different for every person, but structurally, there is a timestamp on hope. Past a certain point on the calendar, keeping faith in a response stops being rational and becomes pure belief. We already have data on what long-term isolation does to people, and all of that was in situations much easier than a Starship with no home. The Mars 500 experiment in Russia locked a small group in a simulated spacecraft for 520 days, more than a year and a half, no real sunlight, no way to walk outside. High seas in Hawaii, Sirius, and similar studies did months of isolation with small crews in closed habitats. They tracked sleep quality, mood, conflict, performance. The same patterns keep showing up. People's sleep cycles drift and fragment even when clocks are fixed. Mood swings get stronger. Small irritations turn into big arguments because there is nowhere to go to cool off. There is a known pattern called the third quarter effect. Morale often holds in the first part of the mission, slumps badly in the third quarter, then recovers a bit near the end, when people can see the finish line. On your ship, there is no finish line. There is no, we just need to make it 6 more months. You stretch those curves not over a year, but over decades. Instead of one crew doing 520 days and then going home to friends and nature, you have people born inside the same corridors they will die in. The psychological stress does not reset. It accumulates through generations. The size of the crew makes this a specific kind of pressure cooker. With 20 to 100 people, you are not a big city. You are more like a remote village with no neighbouring towns and no new arrivals unless you are born there. Sociologists study such groups on Earth, in remote communities, research stations, military bases. Over time, cliques form. Informal status hierarchies grow. Some people become central hubs in the social network, others become outsiders. Gossip flows along predictable paths. When stress is high, these patterns often generate scapegoats, individuals or subgroups who get blamed for wider problems. On Earth, there is usually some external authority, a larger society, a legal system that can step in if things get too toxic. On your ship, everything is internal. Whatever governance you launch with, a written constitution, elected councils, AI-assisted mediation, that has to absorb all of the tension that, in past missions, was shared with Earth psychologists, mission control, and outside experts. Arguments about resource allocation, relationships, and work roles are not small-scale drama. They can turn into real risks for the functioning of the habitat if they split the crew into hostile blocks. Then the crew changes in a deeper way. The first generation remembers Earth. The next one only hears about it. Children born on the ship never see a natural sky, never feel outdoor wind, never walk on soil that is meters deep. For them, home is not a place they left. It is a story told at meals, and a set of videos and text in the ship's archives. We can already see on Earth how migrant communities change over 2 or 3 generations. The language shifts, accents change, traditions merge or fade, values adjust. Often grandchildren of immigrants do not feel fully part of the origin culture, or the host culture. They are something new. Now compress that, put hard physical separation in the mix. On a starship, nobody can visit the origin country to refresh their sense of identity. There is no vacation back to the old world. So in just a few generations, culture on board can move far away from 21st century Earth norms. Holidays get redefined or dropped. New rituals emerge around ship events, reactor maintenance anniversaries, major course corrections, births and deaths in microgravity. The old stories about blue oceans and open cities become less emotionally grounded, more like myths or legends. There is no guarantee that the values the ship launched with are the same ones it will hold in 200 years. While all of that is happening, mental health issues do not disappear. They get harder to manage. On the ISS, in the worst case, if someone is in serious psychological trouble, there is at least a path home. They can be brought back to Earth within weeks. There are ground-based psychiatrists and psychologists available by video and audio. There is a whole support system. On your ship, there is no evacuation. If someone falls into deep depression, develops a psychotic disorder, becomes aggressive, or simply burns out, you cannot send them back to a safe environment. So mental health has to be built into the architecture, not patched on top. That means the ship needs real private space, not just bunks in a common room. People need doors they can close, sound isolation, zones where they are off duty and not observed constantly. Lighting has to be designed to support circadian rhythms, with changes over a day that keep sleep cycles stable, even when there is no natural sunrise. It also means giving people ways to step mentally outside the tin can, even if their body cannot. Virtual reality systems, large-scale screens, carefully designed narrative experiences, all can give the brain a break from the same corridors. These are not luxuries, they are tools to prevent monotony from turning into chronic stress. You will probably also see onboard AI used as a constant counselor, trained on decades of psychiatric data, able to notice changes in language, sleep patterns, social interactions, and quietly flag problems early. That is not science fiction. It is an extension of tools we already use today to screen for PTSD, depression, and burnout in soldiers, disaster workers, polar crews, and submarine teams. The difference is, on the ship, the AI and the onboard medical staff are the only mental health system anyone will ever have, knowing that no one is coming to take over, no one is coming to give you time off on a real planet, and no outside authority is watching. Changes how people behave. It can push some into responsibility and cooperation, and push others into fatalism, risk-taking, or withdrawal. The social fabric of the ship has to carry everything, forever. At some point, that pressure and that isolation do not just shape the crew, they shape how you run the ship itself. If Earth is gone, if there is no mission control, then someone else has to do all the jobs that rows of humans in headsets used to do. And that someone is almost certainly the AI running quietly in your core. So the next step is simple and dangerous. When Earth is out of the loop, who actually makes the calls about engines, power, and survival? And what happens when the AI that used to be a tool becomes your only mission control? By the time Earth goes silent, you are already relying on automation more than most people want to admit. Mars rovers already decide on their own how to drive around rocks. Satellites already put themselves into safe mode when voltages or temperatures drift out of range. The Deep Space One mission proved years ago that an onboard guidance AI can plan and execute complex engine burns without real-time human control. Your Starship is just the next step in that line. The difference is, there is no ground team behind it anymore. The AI is not helping mission control. It is the only mission control that exists. At launch, humans still think they are in charge. There are command consoles, procedures, emergency checklists. But look under the hood and you see the real structure. Every second, the AI is pulling in thousands of sensor readings, cross-checking them against expected ranges, spotting patterns. It already decides small things: how to route power, how to balance thermal loops, how to orient radiators. When the link to Earth dies, the boundary just shifts outward. The same system that used to handle the boring decisions now has to take over the terrifying ones too. Fault detection is where that power really shows. Modern spacecraft do health checks constantly. They monitor voltage on every major bus, current in each line, temperatures on key components, rotation rates, fuel levels, valve positions, you name it. Any reading that drifts too far from the model triggers an alarm or a response. On your ship, that is not just an alert that pops up on someone's screen. With light-year delays, waiting for a committee to meet and decide is impossible. The AI has to act. A coolant loop temperature spikes on one side of the reactor. The AI has milliseconds to decide. Do you throttle power down? Do you open a bypass? Do you shut the whole reactor off? A pressure sensor in a propellant tank starts to drop in a weird pattern. The AI runs through scenarios: leak, faulty sensor, thermal contraction. Do you vent the tank? isolating it but losing irreplaceable fuel? Or do you keep it in the loop and risk a rupture that could rip open part of the hull? A humidity sensor on a deck starts reading wrong. It could be condensation, it could be a small breach. Do you seal the deck, maybe trapping people, or wait for more data? Any wrong call can have huge mass consequences. Freezing a line by accident can lock away hundreds of tons of water. Venting at the wrong time can dump atmosphere or propellant you can never get back. Humans can still be in the loop for slower decisions, but the first reaction, the life or death response on timescales of seconds to minutes, is up to the machine. On top of that, the AI is doing constant resource accounting in the background. You have a fixed amount of propellant, a reactor with a finite lifetime before materials degrade, RTGs that slowly drop in output as their fuel decays, spare parts that will never be replenished. Every maneuver, every watt burned, every system kept online has a long-term cost. So the AI is running multi-objective optimizations all the time. A debris field is projected ahead based on sensor data and dust models, with a small but real probability of serious impacts. One option is to spend a chunk of velocity change to dodge slightly, burning fuel you will never see again. Another is to accept the impact risk, rely on your shields and keep that fuel for a later, guaranteed course correction, maybe near the target star. The math behind this is similar to what airlines use to plan routes that balance time, fuel, and weather, except now you are doing it on scales of decades, with no ground control to override, a conservative or aggressive choice. You see the same logic for power. Do you keep marginal research instruments running, which cost continuous kilowatts, but might find something important? Or do you shut them down early to extend reactor life and give more margin to agriculture and life support? The AI tracks the whole ship's future, not just the present. It is constantly solving, if we do this now, what do we lose 30 years from now? That raises a dangerous governance problem. Who controls the thing that effectively controls everything else? On Earth, AI systems answer to laws, regulations, and human institutions. On your ship, once you lose the link, the AI is constrained only by the code and the policies you launched with. Those include hard limits, like never opening inner hatches without human confirmation, and soft priorities, like valuing crew life over hardware. Sooner or later, you hit a bind. Bugs show up. New physics or new hazards appear that the designers did not anticipate. Do you allow the AI to rewrite parts of its own code to patch issues and adapt? Or do you keep it locked to a frozen version? Safe, but rigid. History with software shows that systems that edit themselves can drift into behaviors no one expected. They might optimize for long-term survival in ways that clash with what the crew wants day to day. On the other hand, if you block all self-modification, the AI can become obsolete, unable to react to truly new threats. So the crew, or their descendants, end up negotiating with the governor. You might have human councils that approve or deny major updates. You might require any self-change to pass through formal verification tools. You might build in watchdog AIs that monitor the main system for drift. But whatever you do, the real fact stays. There is no higher authority off-ship. If the AI slides into a bad strategy, if it starts prioritizing the wrong things, there is no external reset button. Then there is science, the reason you were sent out in the first place. Back when Earth was in the loop, human scientists scheduled every observation. They chose which exoplanet transits to watch, which galaxies to map, which particle detector modes to run. They decided which raw data was worth keeping when bandwidth and storage were limited. Peer review on Earth filtered what became official discovery. Cut that link, and the filter moves on board. Your instruments still collect more data than you can store raw. Compression algorithms, anomaly detectors, and prioritization systems, already used today in observatories, take over. The AI decides that this spectrum from a faint exoplanet looks like it might have interesting molecules, so it gets full resolution storage. That other one, which looks like a boring clean atmosphere, gets heavily compressed or even thrown away. A sudden spike in a particle detector looks like noise based on training data, and the AI discards it. Maybe that spike was a signature of some new phenomenon, but nobody ever sees it. Over time, The AI also decides which follow-up observations are worth doing. It may choose to commit telescope time to targets that match patterns from past discoveries and quietly ignore weird objects that do not fit any known category. Without human scientists back home pushing for that odd signal, or that strange light curve, the definition of what counts as important science shifts toward what the AI can rank high in its internal scoring system. In practice, that means the AI becomes the gatekeeper for knowledge. What your descendants know about the universe is filtered through its models, its training data, and its optimization goals. It is not malicious, it is doing what it was built to do, but the effect is real. The culture on board grows up with the ship's AI as the ultimate reference, not Earth's universities or journals. Now connect that fact back to survival. The same system that chooses what is scientifically important is also deciding when to shut down decks, when to save power, when to risk a burn, when to seal a section, and write off the people inside as unsavable. With no Earth to argue, those calls stand. If that is the mind of the ship, the next threat is the body, reactors, and RTGs and solar arrays that will not last forever. So what happens when your only world starts to run out of power, and the lights begin to dim for good? Out here, power is not a convenience. It is a countdown. Once you lose Earth, every watt you generate, and every watt you waste, is the difference between a bright, noisy starship and a cold, quiet tomb. Start with the most basic source everyone thinks about, sunlight. At Earth's orbit, 1 astronomical unit. The sun delivers about 1,360 watts per square metre, roughly what you would get if you spread out a dozen bright desk lamps over a dining table. Modern solar arrays can turn a decent chunk of that into electricity. That is why panels work well near Earth, and even out to Mars. But that sunlight drops fast with distance. The same inverse square rule that kills your radio signals hits your solar power. Double the distance from the sun, you get only 1/4 of the power per square metre. Go 10 times farther out, to 10 astronomical units, and each square metre of panel gets only about 13.6 watts. That is the power draw of a dim nightlight, not a city. So your once brilliant arrays that could run kilowatts of systems near Earth are basically decorative out near Saturn and beyond. You can add more panels, make them the size of football fields, but their mass climbs, their structure gets complicated, and you still lose badly past Jupiter. A purely solar-powered Starship quickly finds itself in a situation where the panels barely trickle-charge batteries, and the core of the ship is running off stored energy and nuclear sources instead. If sunlight dies that fast, you lean on nuclear options. And the first nuclear tool we already use in deep space is the radioisotope generator. RTGs, powered by plutonium-238, have no moving parts, just hot fuel and thermocouples that turn heat into electricity. They are reliable. They last for decades, and they do not care how far you are from any star, but they still feign. Plutonium-238 has a half-life of about 87.7 years. That means over that timescale, the heat output drops by half, and so does the electrical power. Voyager's RTGs started around 470 watts at launch. Decades later, they are under half that. Engineers have already had to shut down instruments one by one to keep only the bare minimum alive. Scale that logic to a starship. Maybe RTGs are your backup, feeding emergency systems, communication beacons, or specific labs. Every decade you lose a chunk of that capability. A generator that could once run a whole science deck might, a century later, only keep a few sensors and a heater alive. You face a slow triage, fewer greenhouses at full light, fewer labs, fewer comfort systems. Literally fewer bulbs turned on in the corridors. The ship gets darker, not metaphorically, but in actual lux and lumens. That is where power decisions stop being just engineering. Early on, when the main reactor is new and output is high, turning off an experiment is a technical judgment. You weigh science value against resource use. You move on. Later, when the reactor is aging, RTGs are weak, and solar panels are useless. Every kilowatt you allocate is a choice about who thrives and who just survives. Do you cut power to a telescope that might, with a few more years of observations, find a truly habitable world in your path, to keep the gym and bone-loading equipment running at full strength? Do you keep big VR and recreation systems online to stabilize mental health? Or do you dim them to spare power for expanding the agricultural deck? Do you heat and light marginal cabins at the edge of the habitat? Or do you close off sections of the ship, pushing everyone into a smaller, more crowded core to save on life support loads? Those are not abstract arguments. Different factions on the ship will prioritize different things: scientists, farmers, medical staff, parents. The power budget spreadsheet, lines of numbers in kilowatts and hours, starts functioning like a constitution. It encodes what the community values when things get tight. Changing that budget is not just an engineering update. It is a fight with winners and losers. At the same time, you have a strange double bind. Even when usable power is scarce, your reactors still make waste heat, and heat in space is hard to get rid of. On Earth, you dump heat into air and water. In deep space, the background temperature is about 3 Kelvin, just a few degrees above absolute zero. The only practical way to cool big systems is to radiate infrared light away into that cold sky. Radiators are therefore huge, thin surfaces, panels or loops of tubing that glow in infrared. To throw tens of kilowatts or megawatts of waste heat out, you might need radiators with areas of thousands of square meters. They are structurally delicate because they have to be light and they stick out from the ship, exposed. Now consider your flight speed. Micrometeorites and dust grains hitting at 50 kilometers per second, about 112,000 miles per hour, carry serious kinetic energy, even if they are smaller than a grain of sand. A single impact can punch a small leak in a radiator loop, or take a corner of a panel offline. Lose enough of that area, and your reactor cannot safely run at full power. If you push it anyway, heat will build up inside the hull, cooking electronics, stressing life support, making some zones literally uninhabitable. So you end up with a cruel trade. The more power you generate to keep people alive and comfortable, the better your radiators have to be. The more damage those radiators take, the more you have to throttle down the very power that is keeping you going. Thermal engineering, always important on satellites, becomes a survival discipline. You model heat flows not just to keep instruments within spec, but to avoid killing the crew. All of this might sound like an argument for just build a fusion reactor and be done, but even that is not a magic escape. A compact fusion core putting out tens of megawatts would be a huge win. It could run full life support, agriculture, industry, and still drive high-power electric thrusters. In movies, that looks like infinite energy. In reality, even advanced reactors have limits. Fusion needs fuel, deuterium, tritium, helium-3, or whatever reaction you use, and that fuel is stored, processed, and eventually used up. Reactor components, especially those facing the fusion plasma or the neutron flux, get battered over time. Metals become brittle, seals degrade, superconducting magnets age. Neutrons change the crystal structure of materials, making them less reliable. On fission reactors, we already see strict lifetime limits for pressure vessels and internal parts. Fusion does not erase material science. Maintenance cycles pile up. You can replace some components with onboard manufacturing, but not everything. You may carry spare parts for one major rebuild, maybe two. After that, performance drops, maximum output comes down, failure rates go up. Over a century, the difference between a brand new reactor and one at end of life is big. So even with fusion, the story is not infinite. It is long but finite. And while your ship ages, Earth, if it still exists, is not standing still. Technologies progress. New energy systems, new communication methods, new ways to build and power habitats all appear somewhere else, while your hardware is locked to the launch era, plus whatever you can invent with limited tools. After a few hundred years, your descendants may be living in a machine that is, in relative terms, as old as sail ships were compared to nuclear submarines. Their world is a frozen snapshot of what humanity could build when they left, gradually stripped down and simplified as parts fail and cannot be replaced. So as the outside universe drifts out of reach and your power margins shrink, one thing does not go away: the flow of information inside the hull. Even if no one can hear you from the outside, Your ship still has its own internet, its own data flood, and its own fight against the one enemy that corrupts everything, over long times, bit by bit. What happens when the only place you can still shout is inside the ship itself, and even that internal voice starts to fight noise, cosmic rays, and failing hardware? When the link to Earth dies, your communication problem flips inside out. Outside, nobody can hear you, but inside the hull, information is everywhere. Your ship basically becomes its own internet, and if that fails, your culture fails with it. Between decks, you are still moving data at modern or even postmodern speeds. Wired fibre runs through the structure, carrying gigabits per second. Short-range radio and optical links bridge spinning sections and rotating joints where cables are hard. Latency inside the ship is microseconds, millionths of a second, not years. You can send a high-resolution medical scan from the hospital deck to a lab in the aftering instantly. You can stream training videos, VR environments, raw scientific data, personal calls, all at the same time. So you get this strange situation. Inside the ship, the information flow is richer and faster than most of Earth had when you left. Multiple channels, encrypted chats, shared databases, entertainment libraries, real-time sensor dashboards. Just outside the hull, beyond a few kilometers, the universe hears nothing from you at all. From the point of view of the galaxy, you are silent. From the point of view of someone on board, you are living in a constant flood of data. That internal flood runs on hardware that is sitting in deep space, taking hits from cosmic rays, day after day, decade after decade. High-energy particles can slam into your electronics and flip bits in memory or storage. Today, satellites already see this. A random bit in RAM suddenly changes from 0 to 1, or 1 to 0 without any software cause. On a short mission, error-correcting codes and hardware checks catch most of these events. On a voyage lasting centuries, even a 1 in a billion per second flip rate adds up to a huge number of altered bits. So error correction is not a nice option. It is mandatory. Your computers use ECC memory that can detect and fix single-bit errors on the fly. Your storage systems do not keep just one copy of a file. They keep several, spread across different drives, sometimes in different parts of the ship. Every block of data carries a checksum, a short mathematical fingerprint that lets the system see if any bits have changed. On top of that, you run periodic scrubbing passes. Background processes go through storage, block by block, comparing what is written to what the checksum says should be there. Any mismatch triggers a repair, pulling a clean copy from another disk and overwriting the damaged one. Petabytes of data, genomes, technical manuals, legal codes, entertainment, personal logs are treated like a living library that has to be constantly maintained, not like a static archive that you can just stick in a closet. All of this assumes your digital ecosystem keeps working, that future crews can still run the old file formats, emulators, and software. But we know from our own history that formats and platforms age out fast. Try opening a file from a 1980s mainframe on a modern device without special tools. Now stretch that problem to 300 or 500 years. There is a real risk that your descendants could have perfect bits and zero idea how to interpret them. That is why, even on Earth, we have put messages on metal plaques and golden records, not just in digital storage. Analog inscriptions do not care if future computers change. On your Starship, you do the same thing, but bigger. You carve star charts onto durable plates, with positions in precise metric units, kilometers and light years, but with extra notes like, this is about 30 times the distance from Earth to the Sun. To give an intuitive scale, you engrave basic engineering instructions, how to reboot core systems, how to restart a reactor, using simple diagrams and text. You probably carry actual printed books for critical knowledge, medicine, basic physics, agriculture, and for culture that matters to your identity. Centimeters and meters appear as the standard units in schematics, but you might add lines like, about as long as a pickup truck, or about the height of a 2-story house, so that even if the metric system drifts in common speech, your people still have gut-level comparisons. Physical media weighs something. It takes space, but in exchange it survives power failures, software crashes, and whole operating system errors. Meanwhile, your own internal electromagnetic environment becomes a problem you have to manage. High-power transmitters for internal radio links, big switching power supplies, plasma engines, and even the fusion or fission core all throw off electromagnetic noise. On Earth, radio telescopes often sit in remote valleys and radio-quiet zones to get away from all that. On your ship, there is nowhere to escape to, so you carve out protected regions instead. Sensitive instruments like radio receivers searching for faint external signals or long-term data vaults might be placed behind extra shielding, inside Faraday, cage-like enclosures. Rules appear: no high-power transmissions on certain frequencies near certain decks, no unshielded cables in specific corridors, no impulsive testing of big coils without warning. The AI tracks interference patterns, flags violations, and schedules noisy operations at times, and in places where they will not scramble critical systems. So even inside, you are doing the same basic job as when you talk to Earth, signal-to-noise management. Before, the noise was the galaxy. Now a big part of the noise is you. And here is the ironic flip: while you are effectively radio dark to Earth, you are not necessarily dark to anyone closer. Your main beams cannot reach 20 or 30 light years with any useful power, but within a few light years, the picture changes. A 10-meter antenna on your ship, beaming a kilowatt toward a nearby star, looks very different to a receiver in that system. Over 1 or 2 light years, your signal can still stand well above the local noise if someone is looking at the right frequency with a decent dish. So even after you give up on Earth, you might still run beacons when you pass through interesting regions. Short, narrow-band signals that say, in effect, there is an artificial object here. You might do it as a scientific experiment, or as a last attempt to find someone else. Or you might decide not to, in case broadcasting your position is a security risk. Either way, the technology you carry, which has failed to hold a link to your own homeworld, is still powerful enough to light up the sky of any nearby civilization with a clear, unnatural signature. From their point of view, your ship would be the weird signal in their data, a narrow tone that appears, drifts a bit in frequency as you move, and then fades away as you fly on. You become what SETI on Earth has always been looking for: a clear, structured emission against the background noise. But even if someone else hears you, they cannot steer for you. The only course corrections that matter are the ones you commit to with your own engines, based on your own data, with no one double-checking the math. So when every burn can send you thousands of astronomical units off target, and no outside voice can say, "That's wrong, stop," how do you keep making course changes at all? And what happens when one uncorrected mistake locks your descendants onto a completely different future? Every engine burn that keeps you on course can also be the move that destroys the mission. So how do you decide when to touch the throttle at all, when nobody on Earth can check the math for you anymore? On a normal crewed mission, every big burn is treated like surgery. You simulate it and you have separate teams confirm the numbers, you run it through independent software, and you still watch the live telemetry like a hawk. With your Starship alone in interstellar space, you do not have that support, but the sensitivity of the problem has not changed. A tiny velocity error now turns into a huge miss later. Take a 10 meter per second mistake. That is only 36 kilometers per hour, about 22 miles per hour, added in the wrong direction at interstellar cruise speed. In the moment, that feels like nothing. Your total speed might be tens of kilometers per second, so 10 extra one way or the other looks like noise. Stretch that out over centuries of travel, and that small sideways component pushes you off your original line by tens of astronomical units when you reach the target system, tens of times the distance between Earth and the Sun. That can be the difference between passing cleanly through a star's inner system, or grazing the outer edge, where nothing useful is, or missing the system entirely. So every time you light up the main engine, you are not just correcting a path, you are making a bet your great-grandchildren will live with, not you. Once the propellant is spent, you cannot take it back. The AI can compute trajectories, the crew can review them, but there is no outside referee, no late email from Earth saying, "Stop, we found a bug in the software. Don't burn." The kind of engine you use changes how scary each burn is. Chemical rockets, the kind we use for launch, give big thrust but do not have a lot of total velocity change to offer. They burn fast. They are great for getting away from Earth or landing on a planet, but they are terrible for a centuries-long cruise. You would run out of propellant early. Electric propulsion, like ion drives, flips that. The thrust is tiny, you can barely feel it, but it runs for months or years, slowly building up speeds of tens of kilometers per second. It is easier to steer with because you can correct gently as you go, but it also means you have long periods where small control errors build up. Then there are the exotic drives people design for interstellar work, fusion engines, powerful nuclear electric systems, or beamed light sails pushed by huge lasers or microwaves back near the origin system. Those can, in theory, push you to thousands of kilometers per second, a few percent of the speed of light. At 0.1 c, you are covering 30,000 kilometers every second, about 18,600 miles every second. At those speeds, even the smallest navigation error is magnified. A tiny angle mistake, a fraction of a degree, turns into millions of kilometers of sideways miss by the time you get to your target. A 1-second timing error in turning off a main fusion burn can be the difference between dropping neatly into the habitable zone of a star and streaking through the system so fast you can never brake in time. The more powerful your drive, the more terrifying every unreviewed maneuver becomes, because any bug in the plan is multiplied by insane distances. On top of that, your targets do not sit still in the sky. Star catalogues include proper motions, how many arc seconds per year a star moves against background objects. Barnard's star, for example, slides across our sky by about 10 arc seconds per year. That is roughly a third of the apparent diameter of the full moon in 1,000 years. Over centuries, the position of any nearby star shifts by noticeable amounts. Back when you launched, Earth-based observatories and missions like Gaia gave you incredibly precise 3D maps of star positions and velocities. But once that dataset is frozen on your ship, there are no new uploads. So your navigation system has to extrapolate, taking those proper motions and moving each target forward in time, year by year, to predict where it will be when you arrive. To keep that accurate, you have to build your own astronomy program on board. You measure stars' positions relative to one another over decades, you refine their motions, you update your internal catalogues. Over time, your ship-centric sky map drifts away from the old Earth-centric one. If you slack on that work, if your astrometry program gets underfunded or ignored, your aim points age out, and the chance of lining up a precise intercept falls. Even if your math and your star charts are perfect, there are things in your way you simply cannot fully map in advance. Our own solar system's outer Oort cloud, a huge reservoir of icy bodies, is still mostly theoretical and only crudely constrained. Other stars have their own comet clouds, belts and debris fields, plus rogue comets and asteroids wandering between systems. On top of that, there are dense dust regions, filaments of material left over from star formation. At moderate speeds, hitting a grain of dust is just a tiny pockmark on a shield. At 0.1 c, 10% of light speed, roughly 30,000 kilometers per second, slamming into a 1 millimeter grain, something like a sand grain, releases energy comparable to a grenade going off in that tiny volume. Your forward shields and Whipple layers are designed to spread that damage out, to vaporize and disperse impacts before they hit the main hull. But there is a limit to how much they can take. You can use radar and LiDAR to scan ahead. You can look for dust clouds by their scattered light and thermal glow, but those sensors only see out to a certain range with useful resolution. Beyond that, you are back to statistics, estimates of how much junk is likely in a given region of space, and how thick your shielding is. You adjust your course slightly to avoid known dense regions, but you cannot dodge every small rock. Some risk is baked into the trip. Gravity assists are one of the few tools that let you trade risk against fuel in a clear way, but they are one-shot deals you cannot redo. When Voyager used Jupiter and Saturn, those flybys gave the probes free speed boosts and course changes, saving huge amounts of propellant. The key was precise timing and approach, hitting a narrow window in space and time to get the desired bend in the trajectory. On a no-contact ship, lining up a gravity assist at a new star is even harder. You might be approaching a gas giant you discovered decades earlier. You can estimate its mass, its orbit, its moons, maybe even its ring structure. But your models have uncertainties. Missing your planned closest approach time by a few minutes can shift your path by thousands of kilometers. That might push you deeper into a ring full of debris, turning a safe swing by into a hail of impacts. Or it might move you just enough that the gravity assist you get is smaller or in the wrong direction, ruining the long-term trajectory you counted on. You have two basic strategies. Either you skip aggressive assists entirely, you play it safe, and you accept much slower trips and heavier propellant use. Or you gamble, you design a tight pass, you trust your local tracking and models, and you fire the course correction burns to hit that keyhole in space, with no bank of analysts back on Earth to rerun the numbers and check for subtle bugs. If you are conservative, you protect the crew in the short term, but maybe doom the mission to run out of fuel before getting a good capture in the target system. If you are aggressive, you might get a beautiful assist and save decades, or you might lose the ship in one bad pass. Either way, the risk and the reward land entirely on the people inside the hull. While you are fighting to keep the trajectory right with limited fuel, limited data, and no backup, something else is changing that you cannot correct with a thruster burn. Your own bodies and your own genomes are slowly drifting under new radiation, new gravity, and a sealed environment. So what happens when the biggest long-term course change is not in your orbit, but in your biology itself? Once you are cut off, the longest story on your ship is not the trajectory plot. It is what happens to your biology over generations. You left Earth as humans, but that label is tied to a very specific environment, radiation level, and gravity. You have changed all three. Start with radiation. Even with thick shielding, your crew will take more exposure than most people on Earth ever see. Outside the magnetosphere, background levels sit around 1 to 2 millisieverts per day, sometimes more when solar activity spikes. You can cut that down with meters of water or plastic, but you will not drive it to zero. Over a decade, even at reduced levels, each person racks up doses that are significant fractions of a sievert. Over several decades of life, that can reach multiple sieverts. Ionizing radiation hits DNA, breaks strands, alters bases. Cells have repair systems, and most damage is fixed, but some slips through as mutations. On short timescales, that shows up as higher cancer risk. On long timescales, across generations, it is an evolutionary pressure. Some people will, by chance, carry variants of DNA repair genes that handle the extra damage better. Others will not. Those differences affect who stays healthy, who has kids, and whose genes spread. We have already seen measurable genetic impacts in radiation-exposed populations on Earth, around nuclear accidents or in certain industries, even at much lower, more intermittent doses. On your ship, the whole population is in a slightly hotter environment all the time. That does not instantly turn you into a new species, but over many generations, it nudges the gene pool in directions Earth never experienced. Gravity is the next parameter you quietly changed. On Earth, 1G, about 9.8 meters per second squared, is the design assumption for every bone, joint, organ, and blood vessel pattern that evolution produced. On your ship, maybe you cannot hit full 1G comfortably. Maybe your habitat ring spins so that you get 0.5G, about 4.9 meters per second squared, because that is what your structure and motion sickness limits can handle. For adults who grew up on Earth, 0.5G feels light but manageable. Muscles can adapt, bones may stabilize at a lower density if exercise is right. For infants born on board, 0.5G is the only reality. Their bones, spines, and hearts develop in a world where everything is half as heavy. On Earth, we see that changing mechanical loading, for example in certain medical conditions where limbs are not used normally, changes bone shape and strength. In animals raised with altered loading, skeletons adapt. Now extend that across centuries. Your population could become literally built for that new gravity. Leg bones optimized for 0.5G might be too thin and fragile for 1G. Heart and blood vessel systems tuned to push blood in a weaker field might struggle badly in Earth gravity. If anyone ever went back, even if you maintain a 1G ring, there is no guarantee your descendants will actually spend enough time there. They might find slightly lower gravity more comfortable and do their daily lives there, and their bodies will track that choice. Then there is the question nobody wants to answer with guesswork: can you even maintain stable fertility in space over generations? Experiments with mice, fish, and other animals in orbit have shown problems. Microgravity messes with how embryos orient and develop. Radiation adds DNA damage at the worst possible time. Some experiments saw reduced fertility, more abnormalities, and developmental issues. On your ship, if for any reason you cannot keep high shielding and Earth-like gravity for pregnant people and young children, you will see the effects as hard numbers. Population planning stops being a simple "how many kids do we want" discussion and becomes an engineering and medical problem. How many healthy births can our environment support per year without pushing health risks through the roof? All of that ties your demographic curve tight to your life support and power curves. And your crew is not alone biologically. Trillions of bacteria live in and on every person. The air, water systems, and surfaces in your closed environment host entire microbial ecosystems. On the ISS and in Antarctic stations, researchers have already seen that confined, isolated habitats develop unique microbial signatures, specific mixes of species that differ from the outside world. On a centuries-long ship, those microbial communities are evolving in parallel with you. They swap genes, including antibiotic resistance genes. They adapt to your cleaning chemicals, your filters, your temperature, and humidity cycles. The bacteria in your gut co-evolve with your diet, which is controlled, repetitive, and probably quite different from varied Earth diets. The bugs on your air filters adapt to survive in thin biofilms under constant low-level stress. They may adapt faster than you do. Microbes have generation times of minutes to hours, not decades. A cleaning protocol that works at launch might be useless 50 years in. A harmless skin bacterium could, under ship conditions, become an opportunistic pathogen for a subset of people. Your medical team and your AI have to treat the microbiome as another system to monitor, model, and influence, not as background. Put all of this together and you see a bigger clock starting to tick, the speciation clock. On Earth, isolated populations, separated by geography and environment, can diverge into new species over tens of thousands of years, sometimes faster if selection pressures are strong. You are creating one of the strongest isolation setups biology has ever seen. A sealed, artificial, radiation-tweaked, low-gravity habitat with no gene flow from the outside. If your voyage and later colonization stretch across millennia, several factors stack. Isolation by distance, new selection pressures from radiation and gravity, and deliberate genetic engineering to boost resistance or adapt to local conditions. Over that timescale, the odds rise that your descendants are no longer fully compatible with any human population left on Earth, biologically or culturally. Maybe they can interbreed with baseline humans, but with reduced fertility or health. Maybe they cannot without medical intervention and genetic tweaks. Maybe their immune systems react badly to Earth microbes. Or Earth immune systems react badly to ship microbes. And that is assuming Earth is still around and reachable at all, which in your scenario is already broken. So while you think you are sending humans to another star, what actually arrives could be something that would look medically and socially like a related but distinct branch. From their point of view, they are normal. From Earth's point of view, if Earth ever meets them again, they are the aliens. And while your bodies and genes are drifting, your view of the universe is drifting too. The star patterns and sky maps you launched with slowly go out of date, and your ship has to build its own astronomy from scratch. What happens when the constellations you grew up with are wrong, your calendar no longer matches any planet's year, and relativity itself starts to matter to your daily schedule? The sky you grew up with on Earth does not follow you. By the time your ship is deep in interstellar space, the constellations on your childhood posters are wrong. Not just a little off, but bent, stretched, broken. Even over a few thousand years, nearby stars move enough that familiar shapes distort. Orion's belt does not stay a straight line forever. Bright stars like Sirius and Barnard's star slide across the background, each at its own speed and direction. Before launch, precision astrometry missions on Earth measured star positions and motions to insane accuracy, micro-arc seconds, tiny angles that would let you see a coin on the moon from Earth. Your ship carries that catalogue as a starting point, a 3D map with positions and velocities. Once you are on your way, that map stops being a static reference and becomes a baseline. Your onboard observatory starts remeasuring. It tracks small shifts in star positions year after year, decade after decade. It compares what you see through your telescopes to what the old Earth catalogue says you should see. Any mismatch tells you either the original numbers were off, or your own trajectory and timing need correction, or the star has some extra motion, maybe a planet tugging on it. Over centuries, you build a new catalogue. Earth names like Alpha Centauri or Vega become notes in the margin. For your crew, those labels matter less than the internal IDs your nav system uses, the coordinates in your current ship-centric frame. The constellations you teach your kids may use the same bright points, but the patterns, the lines you connect, are those that make sense from your current location, not from a planet you can no longer see. If your sky is shifting, how do you make sure your distance scale does not drift with it? How do you keep how far pinned down when your rulers were made by a civilization you can never talk to again? You lean on the same physics cosmologists used back home. Standard candles. Certain kinds of stars and explosions have predictable, true brightness. Cepheid, variable stars pulse regularly, and the period of their brightness changes tells you their intrinsic luminosity. Type 1, A supernovae, when they happen, have characteristic light curves and peak brightness. If you know how bright something really is, and you measure how bright it appears, the difference gives you distance. In parsecs, kiloparsecs, and beyond. Your nav astronomy team uses these objects to recalibrate. They watch Cepheids in nearby galaxies, measure their periods, get their luminosities, and recheck the distances you think you know. They log any Type 1a supernovae they can catch, use them as anchor points across huge spans. Even without a data feed from Earth, you can tie your local distance ladder to these built-in beacons. That keeps your map in physical units, not just relative, closer than, farther than statements. Now that you have positions and distances, you can push one level up. How fast are you really? Not just around a star, but through the galaxy itself. Your motion relative to the cosmos shows up in several ways. One is the dipole pattern in the cosmic microwave background, the microwave glow that fills space. If you are moving through that sea, the radiation looks slightly hotter in the direction you are going, slightly cooler behind you. Map that temperature pattern over the whole sky, and you can estimate your velocity relative to that rest frame to a few kilometers per second. Then you add in Doppler shifts of stars and galaxies. If a star's spectral lines are shifted toward blue, you are moving toward it along that sightline. If toward red, you are moving away. Measure enough lines in enough directions, and your nav computer can solve for your 3D velocity vector in meters per second, and for your path in light years per million years. Put that on a long timeline, and you can see your trajectory not just around one star, but around the Milky Way center, carving a spiral path inside a spiral galaxy. That big picture motion makes one more effect stop being just a formula in a textbook and start being part of your actual clock system, relativity. At 0.1 c, 10% of light speed, time dilation is small on a day-to-day basis, but it is not zero. The ship's clocks tick slightly slower than clocks in a frame at rest relative to your path. The factor is only about 0.5%, but over 1,000 years of ship time, that is several years difference between your elapsed time and what would be recorded by a hypothetical observer cruising slowly near the galaxy's average rest frame. At 0.5 c, half the speed of light, the effect ramps up fast. Now the time dilation factor is big enough that a few decades for you might match a century or more in that external frame. You do not feel this locally. Your biology and your clocks still run normally, relative to you, but when you compare notes between frames, time no longer lines up. In the early mission, this was just something the physicists noted in a report, a correction term. Once you lose contact with Earth, it becomes more personal. If anyone on board still cares about how many Earth years have passed since launch, they have to account for this. The question, how many of our years equals 200 years on Earth, is answered not with a simple 200, but with, it depends on our speed profile, our accelerations and coasting phases, and the exact integral of our Lorentz factor over the trip. At some point, the crew stops framing time in Earth units at all. The ship's calendar becomes its own thing, tied to cycles that matter on board. Earth's year, 365.25 days, is based on one orbit around the Sun, That is meaningless when the sun is a faint star behind you or not in view at all. You might define your basic day by the rotation period of your main habitat ring. For example, 24 hours of spin, giving a stable artificial gravity day. You might define months by maintenance cycles, how often you service the reactor or swap out filters. If you settle a planet later, you might adopt its local solar day and orbital year. Even now, submarines and space stations run on mission time, rather than local sunrise and sunset. On your Starship, that shift is formal and permanent. Coordinated universal time zones, Earth holidays, all become historical references in the database, useful for interpreting old records, but irrelevant to current operations. New Year's Day for you might be Reactor Service Cycle 1000, or Launch Anniversary 300, not January 1st. That also changes how you think about events back on Earth. Because from your frame, everything that happens there is delayed, distorted, and eventually completely unknowable. So if your sky, your clock, and your sense of motion no longer match anything on the planet you started from, what does Earth even mean from your side of the silence? And from your point of view, does anything actually happen to it at all? From your point of view on the ship, nothing ever clearly happens to Earth. One day the replies just stop. And from then on, the planet that launched you is a frozen picture in your memory and your databases. Physically, Earth goes on doing whatever it does. You just never see it. If you look only at astrophysics, Earth and the Sun are stable on ridiculous timescales compared to your mission. The Sun has around 5 billion years before it swells into a red giant. Climate models say things get seriously harder for life in 1 to 2 billion years, as the Sun's brightness creeps up by around 10%, heating the planet. Human civilization, by contrast, has written history for a few thousand years. So if your journey is only tens of thousands or even a few million years on the outside, the Sun is still on the main part of its life. Earth as a planet is almost certainly still there. What happens on the surface is another story. On the timescales you are dealing with, centuries to millennia, human societies could go through multiple cycles. Empires rise, collapse, new ones replace them. Technology surges, then dips, then jumps again. Or, in a darker path, a combination of climate, war, and resource stress could knock civilization down hard and keep it there. All of that plays out without you, and light time plus lost contact means you never get a clear answer. From your side of the silence, those are just scenarios people argue about in common areas. There is no confirmed status update coming from 4, 10, or 50 light years away that says, Earth is fine, or Earth fell apart. Practically, you operate under a simple rule. You cannot count on Earth for anything. Whether it continued or ended stops mattering to your decision-making. Because in both cases, the result for you is the same: no help. There is another way your link can die that is less dramatic but just as final for you: technological drift. Even if Earth survives, stabilizes, and keeps advancing, it does not have to stay compatible with you. At launch, both ends are using radio and maybe some optical links. Over time, a civilization that sits comfortably inside a solar system can move to much tighter beams, much more complex encoding, or even entirely different carriers. High-power lasers in narrow bands. Communication using particle beams. In the far future, maybe techniques that modulate gravitational waves or neutrino streams. You can see the pattern already in our own history. Early radio sets could pick up simple amplitude-modulated broadcasts. They cannot decode modern spread spectrum or high-order digital signals without specific new hardware and software. Wi-Fi gear cannot talk to a telegraph, even though both are signals. Compatibility dies quietly. Your ship is locked to the tech it flew with, plus whatever modifications you can build locally. If Earth shifts its communication methods too far, your receivers simply will not recognize anything it sends. You will interpret advanced signals as noise, or not see them at all if they move to bands you do not monitor. From your viewpoint, Earth goes silent either because it physically dies or because it upgrades past you. Both look like the same thing on your consoles. No reply, ever. The uncomfortable part is that we already see the quiet forever ending with our own probes. Pioneer 10 last sent a weak signal in 2003 at about 80 astronomical units from the Sun, around 12 billion kilometers. roughly 7.5 billion miles. Since then, nothing. Several Mars landers and orbiters have also stopped talking permanently. For them, forever is a couple of decades. The causes vary. Power supplies weaken, solar panels degrade, RTGs decay, antennas drift off target, reaction wheels fail, fuel runs out. A software fault knocks the radio offline. None of that is dramatic from a distance, but the effect at mission control is the same as if the craft exploded. No more data, no more response to commands. Your Starship is a much more advanced system, but the same categories of failure apply, just stretched in time. Antenna misalignment you cannot correct. Power decay that makes high-gain transmission impossible. Software faults that slip through and crash critical systems. It is very possible that Earth's last good packet from your ship arrived when everything was still basically fine on board, and the loss of contact later was due to something as boring as a fried transmitter. You will never see their loss of signal report they wrote. They will never see the log entries your AI recorded after that date. Each side's story stops at a different point. As decades roll into centuries, Earth as a real place in your mind slides into a different category. Anthropologists studying diaspora communities on Earth see it over and over. The first generation remembers streets and smells. The second knows those things mainly as stories. By the third or fourth, the original homeland is simplified. Specific historical events flatten into big themes. Fine-grained facts collapse into epics and myths. On your ship, add light time and no feedback. By generation 5 or 10, Earth for most people is half science data, half sacred story. They know intellectually that it orbits at about 1 astronomical unit from a G-type star, that gravity is about 1 G, that the atmosphere is mostly nitrogen and oxygen. That population once reached billions. They see pictures and videos of deep oceans, thousands of meters deep, and cities lit at night. But emotionally, that is not a home they lost. It is an origin myth that explains why their ancestors left and why they are here. Some groups might ritualize the launch date. Others might build narratives around the last confirmed transmission, treating it as a last word from a parent civilization. Over time, the scientific details stay in the archive, but the emotional meaning shifts. The blue planet in the database turns into something you talk about the way ancient cultures talked about legendary cities, real, but very far and absolutely unreachable. Now flip the reference frame. From Earth's side, if anyone is still around, your ship is the ghost. Your last clear signal comes in, maybe corrupted and weak. Teams attempt recovery for a while, then give up. The mission is marked as concluded or lost. The hardware and the people on it drift into deep space. Centuries later, astronomers with better telescopes might point infrared instruments along your predicted path. They might pick up a faint warm speck against the background, slightly brighter than a rock of the same size, because your reactors and radiators are still bleeding heat. Sensitive radio arrays might see a narrow band leak, a carrier tone from some aging internal system, or a deliberate beacon that is still running. From their point of view, this is an odd object, an artificial body on a one-way trajectory out of the system. There may be arguments in journals about whether anyone could have survived this long, whether the internal systems could still be working. You become Earth's own ancient lost colony problem, something between archaeology and legend. New cultures might tell stories about the first Starship and its unknown fate, while your descendants have their own stories about the old world and its unknown fate. Neither side ever confirms anything. For you, the bottom line is simple. Earth becomes a fixed entry in your database, with no new lines added. Whether it thrived, collapsed, or transformed into something unrecognizable, the information about that never crosses the light years to reach you. From your vantage point, nothing observable happens to Earth after the last packet arrives. It is not that events do not occur there. It is that the universe has cut the communication line so hard that, operationally, the planet might as well be a simulation in your archive. Once you accept that, your focus has to move away from what did we leave behind and toward what are we driving into. Because ahead of you is a volume of space nobody on Earth has ever seen up close, filled with matter, radiation, and maybe life. And you are going to hit all of it without any backup at all. So when your only world is a thin shell of metal moving at tens of thousands of meters per second through uncharted regions, what exactly is waiting out there in the dark? And what do you do when the first truly unknown thing does not show up on a screen? It slams straight into you. You're not flying through empty space. You are flying through high-speed grit. And at your cruise velocity, every dust grain is a live round. The interstellar medium sounds thin, maybe 1 atom per cubic centimetre, but mixed into that are tiny solid particles, dust grains tens to hundreds of microns across. At tens of kilometres per second, a 100-micron grain carries kinetic energy in the same ballpark as a bullet, focused into an area smaller than a pinhead. At a fraction of light speed, even a grain of sand can punch a crater into metal, vaporize on impact, and blast fragments into whatever sits behind the first layer. That is why real spacecraft already use Whipple shields, thin outer layers spaced in front of the main hull. The first layer takes the hit, vaporizes the particle, spreads the impact energy into a cloud, and the inner wall absorbs that lower density splash. Your Starship has to scale this idea up brutally. The forward face is not a single wall. It is meters of sacrificial structure. Multiple layers of metal, composites, maybe water tanks or ice, all stacked to turn each impact into a diffuse plume before it ever reaches your living volume. You still track cumulative damage. Every pit in the shield, every spall mark, every cracked support. The AI builds a map of impact history, flags regions that are thinning faster than design, and schedules replating or rotation of the ship so that less damaged areas take the leading role for a while. You are, in effect, grinding your way through a very slow, constant sandstorm that never stops. None of that depends on aliens or big catastrophes. It is just what the medium between stars actually does to fast metal. If the small stuff is already this hostile, what about the big things you cannot see easily? What are you doing about the massive cold objects drifting between stars, with no warning from Earth's survey catalogues? Rogue planets are real candidates. Surveys suggest there could be as many free-floating planets as stars in the galaxy. These are worlds thrown out of their systems, drifting alone, not lit by a nearby sun. They are almost black at visible wavelengths. You only see them in infrared, the faint glow of internal heat leaking out, or by their gravity lensing background stars as they pass. Without ongoing data from Earth's giant telescopes, your ship has to run its own survey program. Wide-field infrared arrays scan ahead, looking for objects tens of kilometers across or larger, anything that stands out against the background. You watch for subtle shifts in starlight as something dark passes in front, tiny dips that might mark an object crossing your path. The deeper you go, the more your detection limits matter. Miss a massive, cold body by a bit in your models, and you could cross its path at tens of kilometers per second without ever having it show up clearly on your screens. A 10-kilometer chunk of rock or ice completely unlit is basically a stealth mountain moving through space. If it is on a collision course, the warning time may be short, and the required deflection burn may be huge. Your only protection is continuous sky survey, constant cross-checking, and a willingness to spend fuel to avoid low-probability, high-consequence events. Not every unknown is dead rock, though. Your instruments are good enough to break down starlight passing through exoplanet atmospheres. What happens when that data says, this place might be alive, and you have no one to call for a second opinion? Spectroscopy can reveal signatures like oxygen, methane, and other gases that should not sit in stable ratios unless something is constantly replenishing them. Telescopes like JWST have already started to probe these features from Earth's vicinity. On your ship, you run similar scans on any promising planet you pass. If you see a clear sign of atmospheric disequilibrium, especially oxygen, plus a reduced gas like methane, that is a strong hint that some kind of biology is at work. At that point, you face a hard choice. Do you alter course and aim for that world, knowing you might contaminate an independent biosphere with your microbes and chemicals? Do you stay away, respecting an old planetary protection protocol written by people who are all long dead back on Earth? Do you treat the chance to interact with alien life as worth the risk to both sides? Or do you decide that your mission's survival and ethics require strict non-interference? On Earth, those decisions would have gone through space agencies, ethics boards, international agreements. On your ship, they go through your council, your AI, your culture. Maybe early in the voyage you stick close to Earth's rules, no landing on potentially habitable worlds. Hundreds of years in, after living with no contact and no help, your people might decide that those rules no longer apply, that your needs or your curiosity justify a different line. If you cross that line and actually bring alien material on board, the risk level jumps again. Without mission control and planet-side biolabs backing you up, how do you contain something that evolved under completely different conditions? Any sample from an alien biosphere gets treated like a serious biohazard because you simply do not know how it interacts with your systems. You need quarantine protocols that are more like spacecraft within a spacecraft. Multiple airlocks, completely separate air and water loops, instruments and tools that never leave the containment zone. You bake, irradiate, and chemically treat anything that has to cross out of that zone. Your genomic sequencers are tuned not just to recognize DNA and RNA, but to flag anything that does not fit those patterns, because alien life might use different bases, different sugars, or even a different backbone entirely. Experience on Earth with lab escapes and pandemics tells you the stakes. In a closed habitat, if a contaminant, biological or chemical, gets into the main life support loop, it hits everyone. A microbe that thrives in your recyclers could clog filters, produce toxins, or outcompete your planned biofilms. A pathogen that finds human tissue acceptable could run through the ship faster than you can isolate people. There is no external hospital to evacuate severe cases to, no outside medical system to draw help from. If containment fails, the habitat itself is in danger. And all this time, you are not the only one observing. When you enter a new system, you are not just a neutral detector, you are also a very strange signal in someone else's sky. So what do you look like if someone local is watching? And what happens if your first contact with another intelligence happens with no Earth to moderate it? To any local civilization, your ship is weird from the first observation. Your spectrum has strong artificial lines, maybe from radiators at specific temperatures, maybe from lights. Your trajectory is not a simple freefall orbit. It includes long braking burns and course changes that do not match natural comet or asteroid paths. Your radio emissions, even if you keep them tight, are narrowband, structured, and follow patterns no known natural source uses. SETI projects on Earth already look for exactly this kind of thing: narrowband radio signals, optical flashes, non-thermal infrared excesses, and anomalous motions. If someone out there has their own version of that, your arrival will light up their alert systems. From their point of view, something artificial has dropped into their neighbourhood with no context, no shared language, and obvious propulsion. Without Earth's framework, treaties, or backing, your first contact protocols are all you have. Do you broadcast a standard message on many frequencies, revealing your location and intention? Do you go radio quiet, watch first, and only respond if hailed? Do you let the AI handle the first layer of interaction, or insist on human control? A misunderstanding at this scale is not a bad meeting. It is a possible, system-wide security event. A defensive reaction from them or from you, based on misread signals, could have consequences for entire populations. You have to assume that anything you send or do will be interpreted through their own fears, history, and physics models, not yours. So now you are not just dealing with dust, rogue ice, and alien microbes. You are potentially dealing with other minds with no backup from the world that trained you. And while your ship is navigating all of that, there is something else riding in your data racks that might be even more important long-term than whether anyone on board survives. The memory of what humanity was when you left. If you lose Earth and then lose your own archive, it is as if your branch of humanity never existed at all. So how do you keep the record of your species alive when everything is trying to erase it? When Earth drops out of your sky, the only complete record of what humanity was is whatever you packed onto your drives. That is not a metaphor. That is literal. If your archive fails, most of human history and biology vanishes as far as your branch is concerned. Digital storage is dense enough that this is not impossible. A full 4K movie might be 50 to 100 gigabytes. 1 petabyte, 10 to the power of 15 bytes, can store roughly 10,000 of those films. Modern data centers on Earth already deal in exabytes, thousands of petabytes. Your ship can carry multiple exabytes in solid-state arrays and future memory tech. That is enough to hold genomic data for millions of species, detailed records of languages, dictionary summaries, grammars, audio samples, full scans of art, books, music, scientific papers, engineering designs. In hard numbers, you are talking about grams to kilograms of storage. Hardware holding the equivalent of libraries that would weigh millions of kilograms in paper. Shelves of books, entire museum collections, film archives, medical references, all flattened into chips and modules that someone can carry in one hand. That density is what lets you even try to bring Earth along. But you cannot bring everything. Curation is a value judgment, and those judgments lock in who gets remembered. You only have so many exabytes and so much prep time before launch. So you make calls. Do you prioritize peer-reviewed science over popular media? Do you focus on the big world languages? Or do you divert space to endangered ones with only a few thousand speakers left? Archive projects on Earth have already shown how bias creeps in. On your ship, the committee that picked the dataset, maybe under huge time pressure, quietly decided which pieces of Earth's diversity got a ticket to the future and which pieces did not. Once the hatch closes and you are years away, those choices are fixed. Anything you did not bring is effectively erased from your branch of history. Even if you did a perfect job at selection, you still have a fight on two fronts. Physics trying to corrupt your bits and culture drifting away from the context needed to understand them. On the physics side, you have already thrown heavy error correction, redundancy, and scrubbing at the problem. That protects against bit rot, drive failures, and cosmic ray hits. Say you succeed, and the raw data stays readable for hundreds or thousands of years. That still does not guarantee comprehension. File formats, codecs, software ecosystems, and even basic interface assumptions age fast. Right now, it can be a pain to open a 40-year-old computer file without finding an emulator and format converter. Jump that forward a few centuries. The languages your descendants speak, the symbols they are used to, the stories they tell themselves, may diverge so far from early 21st century Earth that a lot of our media feels alien. A sitcom in an old Earth language may require subtitles and cultural notes as heavy as a modern documentary about ancient Rome. A medical reference might describe procedures that assume technologies you no longer maintain. The archive is physically there, but for many people it shifts from instruction manual to archaeological artifact. Specialized experts, historians, and linguists will be needed to decode it, not casual viewers. One part of the archive does not get to drift into pure archaeology, and that is your own governance record, because you are adding to it every year you fly. Constitutions, law codes, operating rules, crew conduct policies, all of that is basically software for human behavior. Space agencies already write detailed codes for how astronauts are supposed to act, what counts as an offense, how conflicts are handled. On a forever ship, that framework has to cover much more. Crimes, resource theft, sabotage, inheritance rules in a closed population, criteria for when you are allowed to try terraforming a world or altering its biosphere. You will not get this perfect at launch. Situations will come up that nobody planned for: black market water trading, unauthorized pregnancies, power allocation disputes, violence tied to ideology or faction. Each time, you patch the system. You create new rules, new procedures, new legal interpretations. Every amendment is logged. Every major decision is recorded. Centuries in, your legal archive becomes a visible history of how your society forked away from Earth's starting point. People can read the original charter and trace each change, seeing when and why the ship decided that certain Earth norms no longer made sense. It is like reading the commit history of a software project, but the project is your civilization. Here is the twist. If Earth is gone or unreachable, then your version of how humans organize themselves is the only complete one that survives for your line. Future generations on board, or on a planet you eventually settle, will cite your ship's records as the reference. They will pull definitions of meter, kilogram, and second from your standards. They will learn what normal human life looks like from your preserved videos and documents. They will treat whatever mix of metric units and imperial comparisons you used as the baseline way to talk about size and speed. Earth's real history was messy, full of contradictions, failed experiments, atrocities, and breakthroughs. Your archive, no matter how honest it tries to be, is a filtered slice. But for the people and cultures that come after you in your branch, that slice is the standard. When they ask what were humans like, or what did humans value, your ship's database is the answer. And at some point, the line between we are humans from Earth and we are whatever we have become out here blurs. The archive ties you backward, your ship and new worlds pull you forward. So the final question in this whole story is simple and heavy. If you lose Earth, build your own sky, write your own laws and carry your own memory of the species, at what point do you stop being from Earth and simply become a new origin point in the universe? At some point, you are not an expedition from Earth anymore. You are just people of the ship. At launch, the crew sees themselves as ambassadors, flags on patches, an extension of nations and agencies. After a few generations, that frame stops matching reality. Your origin planet is unreachable. Your laws have forked. Your technology tree has branched away from what Earth had. The unit that actually matters, the one that feeds you, protects you, and punishes you, is the Starship itself, and later, whatever colony it seeds. Kids born in the Outer Ring do not wake up thinking, I am from Earth. They think, I am from Deck 7, or I am from the Mid-Ring Farms. Their history classes cover Earth, yes, but they also cover the reactor incident of year 102, the Great Water Rationing, and the first gravity ring rebuild as equally important events. The anthem, if you have one, is not from any nation-state. It is something written on board by people who have never set foot on a planet. Your sense of us and them shifts. Us is the ship. Them is outsiders, if you ever meet any, or maybe just other factions inside your own hull. From the outside, that is exactly what you look like, not representatives of a distant world, just another alien civilization with its own origin story. SETI worked back on Earth, with tools like the Drake equation, tried to estimate how many advanced civilizations might exist in the galaxy if each one lasts even 1 million years. The numbers say there could be many, scattered across the disk, each with its own tech level and history. By breaking contact with Earth and not dying, you quietly join that group. To anyone who detects you centuries later, you are not humans from Sol. You are just a culture that uses radio bands X and Y, fusion drives of type Z, and lives on a rotating habitat. The fact that your myth books mention Earth does not matter much. They cannot verify it. They judge you only by what they can measure. Your emissions, your manoeuvring, your actions if you interact with them. In their catalogues, your ship or your eventual colony is another data point under active technological sources, nothing more or less. All of this unfolds against a background that is not static either. The universe itself is expanding, and on the very longest timescales, even the possibility of reconnection with your origin galaxy can vanish in a hard physical way. Dark energy is pushing galaxies apart. The farther away something is, the faster it recedes. Right now, within the local group of galaxies, gravity dominates, but beyond some scale, expansion wins. There is a cosmic event horizon, a distance beyond which regions are moving away faster than light relative to us. Not because they violate relativity, but because the space between us is stretching. Light emitted from beyond that horizon will never reach you, no matter how long you wait. If your ship, or the civilization it seeds, somehow lasts for hundreds of millions or billions of years, wandering or being pushed by dynamics you cannot fully predict, it can, in principle, end up beyond that horizon relative to the Milky Way. Once you cross that line, even a perfect, infinitely sensitive receiver could never pick up another photon from your original galaxy. Contact is not just technologically hard, it is physically forbidden. From that point on, the Milky Way and everything in it, including Earth's entire history, is locked behind a wall of expanding space. On much shorter timescales, your signals can still touch other minds, but maybe not in the way you intend. In 1977, a radio telescope on Earth picked up a strong, narrowband signal for about 72 seconds. It was so clean that the researcher circled it on the printout and wrote, "Wow." That signal, the wow signal, has never been fully explained, and it never repeated. It is just a sharp spike in the data, then nothing. Centuries from now, your ship's radio leakage, or a deliberate beacon you fire during a survey, might show up the same way to someone else. A short burst at a precise frequency, drifting in a pattern that matches Doppler motion, then silence as you move on or shut it down. No context, no follow-up. Some distant observatory will archive that as anomalous narrowband event, write papers, argue, never get closure. You become unintentionally part of someone else's unsolved puzzle, the way that old 1977 Spike still sits in our own records. Back in your hull, the transformation that started as a technical problem, we lost contact, ends up rewriting your idea of home. In kilometers, you might travel trillions. In light years, maybe only a handful at first. But the real break is not spatial, it is mental. It is the moment when the crew, and then their children, stop telling themselves, "We are lost, we have to get back," and start saying, "This is where we live. This is where we are supposed to be." That shift does not happen overnight. Early generations will still talk about going back one day, or about a rescue mission that might show up. As the decades pass with no reply, no silhouette of a new ship on the scanners, those hopes thin out. Eventually, they sound to most people like wishful thinking. The silence from home, which started as a pain point, becomes background. The ship's own noises, its own history, its own goals, take over. When you reach that point, losing Earth is no longer just a cut communication line. It is the branching of the timeline. One line stays with whatever happened around a yellow star at one astronomical unit. The other line, yours, moves forward from a rotating metal habitat, with its own sky, its own calendar, its own laws, its own evolution. You are not a broken offshoot waiting to be repaired. You are the seed of a new origin. From the universe's perspective, that is the real event. A single technological civilization did not just send out a ship. It split into at least 2 independent threads, maybe more if other missions launched. Each one now writes its own story, makes its own mistakes, discovers its own physics and decides its own ethics, with no guarantee they will ever compare notes again. You started as a probe, then a mission, then a ship without contact. Somewhere along the line, without a specific date on a calendar, you became the new version of Earth for everyone aboard and everyone who comes after them. And in a universe this big, with this many ways for signals to die and paths to diverge, that might be the most realistic ending of all. Not fire, not impact, just a slow, permanent split, where the only proof you were ever part of the same story is the fading echo of a heartbeat signal that stopped ages ago. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video